2, 1. Welcome to the following video for the zonation process on this project. I always spend a lot of time in the introduction, so I will just go ahead and say right now we are following in this landscape prioritization for 10 amphibian species. Right now I am explaining how to set up the software that is going to help us to calculate the best areas, or the gradient of best areas according to the 10 species that we are working with, which in this case is amphibian. The area of study is it's a place close to Mexico City, which is the Mexico state. Hopefully in the end I can show a couple maps so it will give a better context. So so we are going to this map. Hopefully I can show you this result at the end of this whole run. And last time I was just telling you, like, in order to be to do this run, we need to have this BIT file that we will use in zonation. And here we need to have a couple of ingredients to be able to do it, right? So we need to have the setup, the list of species, and where are we going to save that information, where is everything going to be dumped, basically. And the uncertainty parameters, which come in from the distribution models, and if we are going to do some kind of smoothing in the edges, and dispersal information, and something that is like when it finishes, can you close the program or not, yada yada, right? So this is part from the last video. Again, I went through the whole setup, right? But in the setup, I mentioned that we need to have two types of information that is very important, which is the mask. In this case, it's all the localities, either urban or rural, but complexy, let's put it that way. We need to have the uncertainty file. And today, here's where I'm going to try to invest most of the time, which is the file with a list of species. So remember that right now we are working with past, with three sets of time: the past, 1979, current, 2010, and future, 2030, right? Now we will do a run in this case for individual times, and also one that I call interactive one, which is basically like the passing through past, current, and future, right? Now, in addition to that, to that type of treatment, we are also including two types of runs. One where we have information about the importance of the species, or we usually call it weight or hierarchy, right? So we can identify this is more important than this other, right? A lot of the basis of that information was by doing a principal components analysis, where we use conservation status, national conservation status, and international conservation status. For sure you might have heard about the red list. For the national one, there is a decree called the NON 059, right, in Mexico. And yeah, it's that thing about like endangered, critical, and so on. The other component was the CITES, which is the commercial use of the species. We also did, I'm not going to spend my time with that. We developed what we call the distribution index, meaning how likely or how well covered my species is in the area of interest. Actually, if we look on this map that we have over here, where is it? Not a map, but is one of the models, the distribution models. Blue is where we might not have it, red is where we might have it. So this model is based on a lot of pixels, right? And obviously, the higher the number, the best potentiality. Let me just turn off. Let me turn myself off. There. Now you can see it. So in the red areas, we will have a higher score. Fine. So what we did is we took all the numbers from all the pixels and we basically did an average of the whole map. So if the average has a higher value, it means that my species is well represented in the area of interest. Again, if the number of the average of all the values from the model is high, close to 1, means that the species was well represented. If it's lower, it's the opposite. Just by looking at this, I would actually expect to have a lower, less than 0.5, in terms of my distribution index, because it's pretty obvious. There are very few areas where we have the environmental conditions appropriate for that species, and it makes sense because it's an amphibian, and amphibians tend to have a very restrictive distribution. Good. So on that treatment, we use that weighted thing that is composed by all the elements that I just mentioned. Also, we use an estimated dispersal information. But for that one, for this particular set of species, the amphibians, we were not able to use like a proper number, right? There was a publication that we tried to use that more or less gives the estimated, but according to class. But we basically just set a number that tells us there is dispersal capability for the given species, right? So, and the second treatment here is without using that information. What that means is the assumption that all the species are equal and all the species are static. So technically it's not a very realistic scenario, but it's the scenario that could create less controversy in a certain way, because we are not making like big assumptions as this whole class has this dispersal capability and this species has more importance than this one, right? So we're going to be working with those two. Then, well, as I mentioned before, the output folder where everything is going to be dumped. And if you see, well, just one more thing, here we have the 5 columns, right? So the first image that we have here, we can see, the score value based on 1, right? Now the number 2 is the column where we could have used the dispersal information. If I use 1, it's going to be assumed that it's a static. So the only thing that we did is to use the number 2, just to have some kind of assumption that it moves. Then the following information, the uncertainty parameter, this is something that we created back when we were doing the modeling, right? Actually, I think I can show you that. I have it maybe ready. Do I? No, I don't. This process, wait, is it this one? Yeah. So if you watch the past videos, during the calibration, no, during the projection, we indicate to the projection, please create the uncertainty map. So because we worked with, we created a lot of models. We wanted to have the best models, or the most informative ones at least, meaning that based on the TSS statistic, the ones who were 0.05 and or less, those were going to be accepted. Yeah. So because we use 8 different types of algorithms, yeah. So each one of those created TSS. And even though when we ensemble to create the final model, there might have been some of those that were close to not be within the significance that we wanted. And that's where the clamping mask is coming from, right? As it says here, right? It identified the locations where the predictions are uncertain, right? So because it's closed out to be out of the calibrated information that we wanted, right? The evaluation that we wanted. Then following is just a smoothing process. So it will allow to have, it's like a calculation of nearest neighbor. So we don't have like a very cutting edge dispersal information when we are doing the prioritization. Then the multiplying factor here, it was going to be 1, because this goes again into the number 1. Let me just check if that is true. So it's the output. So yeah, so we multiply by 1. No, so hold on. So it's the output, uncertainty, smoothing, and dispersal multiplier. I have to be entirely honest, I don't remember at this time why we decided to use the 180. Hopefully, if I can bring the explanation, I can put it on the description or something. Because in the end, we also try to play very arbitrarily when we use this, some of these factors, because the multiplier is not based on meters or kilometers, right? So I have apologies over there. I do not remember right now what was the reason behind the 180. Then is that setup. It is like after the run finish, can you close it? Yes or no? And finally, the file format that we wanted to have, which in this case, the main one was in ASCII. So once we have the BIT file ready, we can run the project. So that's exactly what I'm about to show you right now. So here we have the whole project ready, right? For this video, I will be just running the times separately, because I did test this one, and I need to check if one of the files for interactions, which you can check a little bit of the concept in the past video, I think I have something written that is incorrect. So basically what we do is just open the project, and then we come over here to the setup that we want. Actually, I still have the old files from the last project, because we tested the with weight, no dispersal, no weight, no dispersal, dispersal, and blah, blah, blah. So we did a combination. So here I am using, I will be running dispersal information and weighted information. Let's go ahead and do it and run quick. It's going to be super fast, and you will see it. You will check out how is it going to do it over here. So you need to remember this. This process, it was based on eliminating where we have the lowest score from the 10 distribution models, right? The lowest score from the 10 distribution models, and that's the first cell that is going to get out. Or in my case, because that's how it was set up, the first 100 cells will be removed. The lowest 100 cells will be removed, and then again, and then again, and then again. So it already finished. I know it is absolutely, it looks weird. Let's use hot. Okay, well, I think it's going to be better if I show you this in ArcGIS. I'm just going to leave here because I have the example ready. I will just let them run. They will be running. So let's go to ArcGIS now and explore a little bit of the results, right? So as you saw in one of the slides, this is the final product. One of the final products, specifically the one using the future scenario, right? So what my result here says is everywhere where I have red is the most ideal, right? It's the highest priority, right? Which is kind of immediately interesting. Let me see if I can bring, do I have it over here already? So I have the mask. So I would say that it would be logical that all these spots over here, those are localities. And it makes sense because localities were used as some kind of mask. So it's like omit this area, right? I see it all in zero, so I'm gonna put it on black. Let me turn it on. Boom. So you see, so it's obvious. It's kind of obvious that we don't want to, at least in this way of thinking, that we should not be prioritizing those areas, right? Now, the way that we set up, we can set up the type of goal or the amount of territory that we want to prioritize, right? So let's say no. Manual interval. Yes, thank you. So I think right now the international CDB, it's trying to suggest to protect at least 10%. Back in 5 years ago, it was like 17%. So I'm going to do the 17%, okay? Now, if I only, can I mess you up? So, well, it's actually almost there. I'm going to leave it close. And I am going to change, just for the sake of changing the color, to white. And I'm going to eliminate, oh God, I'm going to eliminate these two. Close. Okay. Can I remove this? Yes. Okay, so that's it. I will try to present a little bit more revision of these results in the following videos. But if we wanted to see the 50% of the territory, where should I be focusing a little bit more in terms of feature conditions? This is it. So what do we have around here? So one of the first things, yeah, so I have mountains, I have volcanoes. So I have the volcanoes, right? Just kind of cool. Let's compare this to at least one of the distributions, okay? So, hold on. hold on. So I'm just gonna have it less transparent. Yeah. There we go. No, it was not a good idea, guys. This was not a good idea. Okay, 60%. And change the color of this guy. Okay, yes, I'll use that. I mean, you kind of see it, right? You kind of see it, like in this case, for this particular species, the red areas, all these red areas kind of have a little bit of the sense of the prioritization, except all these outside lines. But I would say that these outside parts is basically because you have no locations, right? Let me see if we can check out another one. Can you give me now time? I'm just gonna do one more and that'll be it. So here, so this one, for example, is like pretty not opposite, but we do have a little bit of good environmental conditions here, but this one moves a little bit more to the northwest. You see, and you do have a couple areas to be prioritized necessarily. So we have something, right? Now just keep in mind that this is one of the times isolated. For the following video, we'll go ahead and discuss the other time periods and all, and we'll be talking a little bit of the comparisons among like the distributions and the results. And then we will do the one for the interaction. Right? But as for now, I think this is it. I will leave it over here. Thank you very much. At least the cool thing is that I'm having a couple of results. I know that this is always like very raw and sometimes I miss some of the explanations. But yeah, this is at least the most natural way that I can present it. If there are questions, please go ahead and do it, and then I will go ahead and get ready even more, right? So I can, maybe I explain something, or maybe you can correct me on something, okay? But until then, thank you, and see you in the next. Bye-bye.